Yeah, the dumb little ding means that we are indeed going to be recording things, hopefully. And as soon as this comes on, we'll hopefully get started with some notes that actually are completely new. Um, so you guys should remember that in algebra and geometry, one of the things that got brought up was the idea of similar shapes. Now, since I said I'm recording this for the people that are quarantining, that actually happens to be the very first of the topics you did online last spring, right after state basketball, dealt with similar shapes in geometry. Similar meant things that were the same size but had different shapes. And you solve problems in geometry where you would like set up proportions and cross multiply to figure out how big missing parts of those similar shapes were. And the idea actually comes up in algebra because cross multiplying is like the easiest thing ever in math. But we did a lot of it last year in geometry. Well, it turns out that an awful lot of advanced math is based on that idea. And when we did have similar shapes, it always turned out that the corresponding angles were always the same and the corresponding sides were proportional. Basically, it was like you took a small shape and you blew it up so it was the same shape, but it got bigger. And, again, you might vaguely remember when you were, watching those horrible videos of me last spring, that the very first of those was actually about similarity. I actually was looking to make sure it was literally the first one. I was looking at the YouTube stuff today, and that was the one where I actually had a picture of the Pepsi stuff to start everything off with. So, and that's because a lot of years, if we do it live, I'll haul out the Pepsi stuff and we'll compare sizes of like different bottles and cans and, see how they compare to each other. Well, strange as that might seem, it actually has a lot to do with where we're going. Because what we're going to be studying probably until about Halloween, there'll be 2 or 3 sort of chapter breaks where we'll split things up for that. But we're going to be learning about what's called trigonometry. Trigonometry, the word literally means triangle measure. You might remember last year geometry meant earth measure. And trigo is just the Greek root that means triangle. So it's like the study of the measure of triangles, and it's all based on the fact that if you have triangles with the same angles, they have to be similar. Now that doesn't mean that you're going to like be setting up proportions and cross multiplying all the time, although a lot of what we do is based on someone else having done that to come up with the theory, but it is going to end up being based on triangles being similar. And I don't know that you need to write this part down, but the idea is that since you do have stuff that's proportional, you can always find ratios of the sides, and they're going to be the same no matter how big the triangles are. I mentioned to you that hopefully, like next week or the week after, we're going to be doing this measurement activity where we go outside and we do things like figuring out how tall are the baseball lights or the football lights. They're actually the same height. Softball ones are shorter, but we go and we measure those different things, and well, there's always somebody that volunteers to like climb up to the top of the pole and drop a tape measure from there. Much as Drew would like to do that, usually we try to err on the side of safety. And so what we do instead is we measure some angles and some shorter distances. And once you know that, you can actually figure out a big triangle that would be similar to the small one that you're doing. And using this idea of trigonometry, it's real easy to find out how tall things that you can't measure directly would be. And so that is where we're going to go. And it turns out that trigonometry becomes especially important when we deal with right triangles. What's a right triangle? I know that's a stupid question, but you tell me, what is it? A triangle with a right angle, absolutely. Yeah, that's all it is. And in this picture, you notice they all have the little box in there to show that. Technically, of course, you should, although I'm going to tell you, you're going to see a ton of pictures in this chapter where it's not marked, but we are indeed going to assume that they're right triangles anyway. Before I get into what's actually new with trigonometry, I want to review some terms with you. One of those terms that you learned back in junior high is the word hypotenuse. Big long word. Who knows what the hypotenuse in a right triangle is? Go ahead.
The side opposite.
That sure works. In fact, here's a picture of it. That is definitely the hypotenuse, and it certainly is opposite the right angle. There's also something else that's important about the hypotenuse in a right angle, and that's that it's always the longest side. It's across from the right angle, and it is the longest side. The reason it has to be the longest side is one of the rules you learned in geometry says the longest side of a triangle is always across from the biggest angle, and the shortest side is always across from the smallest angle. So 90 is going to be the biggest angle in a right triangle. The hypotenuse has to be the longest side. Does anyone happen to remember from, back in junior high, what you call the other two sides of a right triangle? Yeah, they come up way less often, although that's suddenly going to become more important this year. The other two sides are called the legs. Those are the sides that form the right angle. They're also the two shorter sides. And the idea is you probably remember things like the Pythagorean theorem that if you take like a squared plus b squared, it equals c squared. Well, the legs are like a and b, and the hypotenuse would be c. So the two shorter sides, if you square them add up, you get the hypotenuse squared. Of those terms, hypotenuse is way more important than legs because we're going to become more specific about the legs here in just a second. And that's because in trigonometry, we will often use the words opposite and adjacent to tell which leg we're talking about. Everybody see the angle that's marked at the bottom left of that triangle, which happens to be named with the Greek letter theta. We'll get into that later on. It doesn't really matter though, it just means angle, okay? So you notice that they have the words opposite and adjacent in here. All opposite means is across from an angle. And if you look at the angle that's marked, yeah, that's across the triangle from there. That's what opposite is. Adjacent just means next to, and I'm going to put those officially on the next couple of screens, but that's the leg that's next to the angle that's marked. Again, opposite means across from some angle. So like in the one on the left, the side that's got to be opposite would be PR. And in the one on the right, the one that's opposite what's marked would be B. Okay. And opposite just means straight across the other side of the triangle from where the angle is. That's what you're always talking about. And adjacent does mean next to, so you're looking for the leg that actually is part of that angle. Now, sometimes people will get goofed up on adjacent because the hypotenuse is also next to the angle. But we're talking about like the shorter side that's next to the angle. We're talking about the leg that would be next to the angle. In both of these, it's the bottom that would be adjacent. You could, however, turn triangles in any direction, and it could be any of the shorter sides that you could have. So I got a couple of quick questions for you. Here is a triangle, and I want to know how long various things are. How long is the leg opposite to A, adjacent to A, opposite B, and adjacent to B? So who can tell me how long is the leg opposite A? What would that end up being? So I'm going to go with Grant back there. And that sounds pretty good because you see A at the bottom, straight across the triangle is going to end up being 5. How about adjacent to A? What would that have to be? Yeah, because it's the bottom this time. Then we have opposite B. Who knows how long the leg opposite B would be, Gavin? That is going to be 12, yeah. Something that'll always happen is what's opposite one angle is going to be adjacent to the other. That is always true. And adjacent to B, next to B, is going to be 5. And so, yeah, there's the different ones that we should have with those. So here's one more set of questions. Same basic things. How long's the leg opposite A, adjacent to A, opposite B, and then I said hypotenuse. We're going to start with the bottom one. How long's the hypotenuse? So what is that? Yeah, 109, sure. So now let's do opposite A. Yeah, because it's the bottom. Yeah, from A down to the bottom would be 91. Adjacent to A should be how long? Yeah, 60 is right. And opposite B is also 60, sure. And that is absolutely correct. Okay. Everybody follow those three terms, opposite, adjacent, and hypotenuse. I really want to drill that in because pretty much everything we do for like the next month is going to revolve around those three terms. And so it really does become kind of important to know that. And we always are talking about one of the acute angles when we use those. You're never going to be asked about something referring to the right angle because if you think about it, like the hypotenuse is what's opposite it, and both legs are adjacent, so that doesn't really make a lot of sense with the right angle. So that's going to lead into what we call the trigonometric ratios. And this is pretty much what the next couple of months are actually going to revolve around because the trigonometric ratios are just ratios or fractions that you can make out of the sides of right triangles. In the picture at the bottom there, you can actually see the abbreviations we use to talk about these, and I would guarantee you've seen those like on a calculator before and probably didn't really know what was going on with them. So here's where we learn. They are called the sine, the cosine, and the tangent. And we will learn all about them here as we go through the next few minutes. So the first one is the sine. And officially, the word sine is spelled out S-I-N-E, although invariably we abbreviate it so it looks like sin. You know, this is the class you get to sin in, but that's a... And it tells you that the sine is the opposite leg over the hypotenuse. And I basically have the exact same thing written three different ways here. I abbreviated that to op over hype, and then O over H, which you're going to end up finding there's a reason why I wrote it that way at the end. Okay. So the sine, again, is going to be a fraction. And if I wanted to find like the sine of B, I go to that picture and I would figure out opposite B is 60. The hypotenuse is 109. And so the sine of B would be 60 109ths. It's a fraction. And very often it's kind of a weird fraction. That's okay. It ends up being a really useful fraction as we go through some different things. You guys see where I'm getting 60 over 109 for the sine of B? Anybody tell me what the sine of A would be? Which is just a different fraction. Grant. 91 over 109 is exactly right. Because if you look at A up at the top, opposite's going to be down at the bottom. That's 91. The hypotenuse is still 109, so 91 109ths is all it is. Okay? So sine is opposite over hypotenuse. How many of these did I tell you there were? 3, yeah. Now I will tell you later on, we're going to find out there's actually 6, but 3 is what we get to use most of the time. So the second one is the cosine. Cosine, again, you see the full word up at the top, but invariably we abbreviate it cos. And it tells you the cosine is adjacent over hypotenuse, or edged over hype, or A over H, adjacent over hypotenuse. So like if I wanted to find the cosine of A, I'd find out the short side that's next to it, which is 60. The hypotenuse is 109, so the cosine of A would be 60 over 109. What's the cosine of B? 0. 91 over 109, absolutely. Yeah. And it will always turn out that the sine of one angle is going to be the same as the cosine of the other. That will always be true. So yeah, again, I'm just taking these 3 sides and coming up with some fractions I can make out of them. And sine was opposite over hypotenuse, cosine's adjacent over hypotenuse. Okay? We good with those two? And the third one was what's called the tangent. So tangent is abbreviated tan. And it tells you the tangent is opposite leg over adjacent leg, or opposite over adjacent. I will also tell you of these 3, tangent ends up almost always being the most important of them. We will use all 3 of them, but when we do things like trying to measure how tall the baseball lights are, those are almost invariably tangent problems. And they're really easy if you figure out how tangent works, but yeah, it is opposite over adjacent. So like the tangent of B is going to be 60 91sts, 60 over 91. Opposite 60, adjacent's 91, that's my answer. What's the tangent of A? Tan A. I'm just looking to see if we have a couple of other people, but since Grant's all excited there, we're going to go with that. Because you just flip it upside down, and that's right. Yeah, it is. Opposite this time's 91, adjacent 60, so 91 60ths. Okay? Now, what you're going to be doing a lot as we go through this chapter is figuring out sines and cosines and tangents of various angles. Sometimes it helps people to like literally write O and A and H next to those numbers in the triangle, so you can figure out exactly what we're talking about as we go with things. You don't have to do that, but it does sometimes make it easier. It also sometimes makes it easier if you especially label the hypotenuse, because you want to make sure that you don't confuse adjacent and hypotenuse. Again, adjacent's always the shorter one of the ones that are next to an angle. So yeah, sine is opposite over hypotenuse, cosine's adjacent over hypotenuse, and tangent is opposite over adjacent, like it says there. So every math teacher who's ever lived and every math book that's ever been written always uses this abbreviation as a way of remembering the trig functions. You tell me, what does this abbreviation stand for? SOHCAHTOA. Yeah. Mm-hmm. Yeah, it's just a quick way of putting all that stuff that I just said all in one place. Sine is opposite over hypotenuse, cosine's adjacent over hypotenuse, and tangent's opposite over adjacent. And when I was a kid, I actually had a teacher that told us about the wise old Indian chief SOHCAHTOA. And that was the way that you could remember all of those things. I've also heard that if you like hurt your foot, you've got a SOHCAHTOA, which is, kind of an Allers joke, but it does still help you remember the basic phrasing of that. You will want to remember those three things. Sine is opposite over hypotenuse, cosine's adjacent over hypotenuse, and tangent's opposite over adjacent. The very first time I taught this, I had a student who carved SOHCAHTOA into the back of his calculator. And that kid went on to be a very successful doctor, so I guess it actually worked out for him. He's out in Maryland right now, actually, and working as a doctor there. So that's, but SOHCAHTOA is the basis of everything we do in trigonometry. What you're going to do today is a really quick little worksheet that just is showing you some triangles and asking you what's the sine and cosine and tangent of various angles, just to make sure that you do that. And it's a very quick little thing to do. Then next week, we're going to go on and say, okay, if I know how to find it, now what do you do with it? How do you actually make that work out for you? So SOHCAHTOA, sine, cosine, tangent. We all good with those? And we'll stop there and move on from